Hi there. Like I said, I wanted to talk about hypothesis tests for population means. This is very similar to hypothesis testing for proportions, so it'll look really, really familiar. So I'm going to kind of go through it a little quick, and then I'll make one more video that talks about an example. I think I'll probably just do one example, and if you want another example, maybe we can do one in class or something like that real quick. But um, we can use things that we've got there if we need to. So let's take a look at this. Hypothesis testing for a sample mean. Remember here that we use the student's t-distribution to construct confidence intervals for population mean, and we also will use the t-distribution to test hypotheses about the population mean. So again, remember that for sample means, we have things that we need to check on to make sure that we can use these tests, right? So that we can use a normal distribution. So the number one was that it's a random sample again. So simple random sampling or from a randomized experiment. The second one here, remember for this one is n is greater than or equal to 30. So hopefully we have that, or we can have a normal population. So if it's given in the problem, population, let's try that part again. If it's given in the problem that we have a normal population, then we're good, right? Remember, there's also the alternatives that we can do the QQ test and look for the outliers using the box plots. And if you want to see how to double check this, if we have a sample under 30, go back and take a look at the previous section. And the third one is that the samples are independent from each other. Right? Again, step one is determine the null and alternative hypotheses. And we again have the same choices. We have a two-tailed where we have the not equals. We have the left-tailed for the less than, and a right-tailed when we have our alternative hypotheses that's greater than. Now remember, your book here is using H1. This is the same thing as my H sub A that I use. They're equal, okay? So if I write an H sub A instead of an H sub 1, it means the same thing. We want to determine the level of significance alpha depending on the seriousness of making a type 1 error. You'll remember that I said if it's something critical where I definitely don't want to make a type 1 error and I don't want to have that error, then I need to make sure that my alpha is low. If it's higher or less serious, then I can use a higher alpha value closer to 0.05 or 0.1. We'll zoom a little bit. So we have the classical approach here where we use the t-statistic, and it says to use the, so we calculate the t-statistic using this formula right here. It follows the t-distribution, remember, with n minus 1 degrees of freedom. And we can use a table to determine a critical value and make a decision. We can also calculate the p-value. Again, we calculate the test statistic. We have a t-distribution with n minus 1 degrees of freedom. This one has you using a table to find the p-value. We're going to use StatCrunch to do it. So technology on step number 3 is the one we're going to use using StatCrunch. Okay, then if the p-value is less than alpha, we reject the null hypothesis. If the p-value is greater than alpha, then we are going to fail to reject. Remember, we can't accept the null. We're just going to fail to reject. Given the amount of time, I'm going to go ahead and do the first example here. So if we take a look at this, a fast food restaurant manager wants to see receipts per car traveling through the drive-through increase. Historically, cars typically spend $13.20. After implementing a new sales process to be used for cars using the drive-through, the manager randomly selects 35 cars and finds the mean bill of $13.96. The standard deviation is $3.69. Does the sample evidence suggest the new process results in higher receipts per car? And here we're going to use an alpha equal to 0.05 level of significance. So if we start out, we're going to have our null hypothesis, which is going to be historically, cars typically spend $13.20. So here, we're going to say that the population mean is 13.20. Okay. And this manager wants to find out, does the sample evidence suggest the new process results in higher receipts per car? So our alternative hypothesis is going to be that the new mean is higher. So it's higher than $13.20. So this is going to be a one-tail test. Okay. And it's going to be a right tail. Alrighty. So let's look at our conditions for number 2. So our conditions, first, we want to take a look at whether or not it's a random sample, and we note that he randomly selects the 35 cars. So as far as a random sample, it looks like we're good. The second one is our sample size. And here you'll note that our sample size was 35 cars that he randomly picked. So n is equal to 35, which is certainly greater than or equal to 30. So we have an adequate sample size, right? And then the last one is to look at independence, and we're going to use the same rule that we used before. Our sample size needs to be less than or equal to 0.05 times the total population size. So here we're going to say 35 is less than or equal to 0.05 times the population size. And so if I divide both sides by 0.05, I get that n must be greater than or equal to 700. And I'm going to guess that we have more than 700 people going through the drive-through over whatever period of time he's looking at. So from this, we're going to say we can assume that the distribution is normal. All right, so we have a normal distribution, and the next thing we want to look at, if you look back up here, way back up here, is that we're going to select our alpha. And if you look, that's actually given to us right here. So I have an alpha equal to 0.05. Let's make that look less like a 2. So I have alpha equal to 0.05. And then the next thing I want to do is calculate my t statistic. And in order to do that, if you remember back to your t statistic, my t statistic is equal to my sample mean minus my population mean all over my standard deviation for my sample divided by the square root of n. So I need to get a little bit more information out. So here we have n equal to 35. Our sample mean bill is x bar is equal to 1396. Our sample standard deviation was s equal to $3.69. I almost made that a 96, 69 cents. And I think we have everything we need. Notice this mu is equal to this mu right here is equal to our population mean that we're assuming. All right. So we can pop in our numbers, and we have 1396 minus 1320 all divided by our sample standard deviation, which is 3.69, divided by the square root of 35. And if you pop that into your calculator and you get everything right, it should be 1.2185. And we want to bring all of those digits with us. So remember, try and bring 4 digits. It's going to help you with your accuracy when you go over to StatCrunch. So if I think about what this looks like when I'm looking at my t-distribution, right? I'm looking at something that looks like, oh, that was kind of rocky. My t is over here. This is a t equal to 1.2185. So I'm looking for the area under the curve over here. So I want the probability that t is greater than or equal to 1.2185. And that is going to be my p-value. Okay, notice the probability p-value, you kind of see the correlation there, right? So what I can do then is if I go over to StatCrunch real quick here, and we close out from the last one that I did, if we go to Stat, Calculators, and then we go down to T, not FT, then our degrees of freedom, we had a sample size of 35, so we can actually type in here 35 minus 1 if we want to. What I want to know is what's the probability that my t is greater than or equal to 1.2185, and I need to change this to a greater than or equal to. So I want that side. That looks exactly like my graph. And what I see is that's 0.1157. So if I come back over to, if I come back over here, I find that my probability is equal to 0.1157, which is definitely greater than 0.05. So here we're going to fail to reject. Now I can use this t-statistics, much like we did before with the null hypothesis when we were using the proportions. It's a little bit easier, or a little less work. So let's go back over to StatCrunch and take a look at that. This time I'm going to come in and I'm going to do stat. Instead of going to calculators, I'm going to go down to t-stats. I'm going to choose one sample. I have a summary because I don't actually have the data. I'm going to put in my sample mean, which here was 13.96. I think I've typed in 5. There we go. My standard deviation was 3.69. My sample size was 35, and it's going to do all the work for me now. Now here, I'm going to say I want to do a hypothesis test. Remember, we did this for confidence testing. Here we're doing a hypothesis test. And what we want to do is we want our null hypothesis to be that mu is equal to 13.20. This is straight off of what you wrote down. And our alternative hypothesis is going to be that it's greater than 13.20. So we want to change that one. We're going to go ahead and click compute. And what you see is, again, the p-value is over here on the right-hand side, 0.1157. Our t-statistic is, again, 1.2185. So if we go back, we have the exact same conclusion that we did before. So if I wanted to write this up, let me add a page real quick. If I wanted to write this up, what I could say is that there is not evidence to support rejecting the null hypothesis. I'm going to try, yeah, here we go. Hypothesis, or you could say we fail to reject the null hypothesis. So the, let's see, the new process or how about there is not evidence, here, let's try this again. There is not evidence to suggest the new process, sorry about that, results in receipts higher per car. Sorry, I keep moving it. I'm trying to put it back. Per car above $13.20. Make it a little smaller for you. So that's really all I have on that one. I think that probably gives you a really good idea of what it looks like. You'll notice it's exceptionally similar. I may do one more just to show you how to do it with the data. I think there's a data one on the test, but I will check that before I look at that. There's not really that many more things on here. One real quick thing that I will mention that's very, very end here at the very end is practical significance. The idea here, we'll stop here. The idea refers to small differences when the statistic parameter is stated and the null hypothesis are statistically significant, but the differences may not be large enough to cause concern or be considered important. So one of the things you see is when you get exceptionally large sample sizes. So if you look down here, when you get exceptionally large sample sizes, they can lead to results that are almost always statistically significant. And so the difference between the two values, the statistic and the parameter, the thing from the sample, which is the statistic, and the parameter, which is the population value, it will show that there's a difference because it's such a large number of samples that you took, but really the difference between the null hypothesis and what the change was is not significant. So it would be like the difference of if I took, let's say, grades from thousands of people and I compared them, I would be likely to get a statistically significant result that there's a difference between two things if I change something just based off of, let's say, a grade difference of 89.9 versus 89.8. So we do need to watch just a little bit whether or not it matters. So you got to kind of do that whole, does it really matter? Is it practical to think that it makes a difference in the real world? So I just thought I would throw that in there. In our previous one, it doesn't really apply, but there are times that it does. And so I thought I'd mention it. So I hope you have a good day, and I will probably put up the one just to show you how to do a small sample with the mean difference, and then we are done. Have a great night. Bye.